Okay, we are good.
Okay, great. All right. So shall we get started?
Yeah.
Okay. So today I'm the host for this 3DGB session. Today our speaker is Qixing Huang, who is an assistant professor at UT Austin. Prior to that, he obtained his PhD from Stanford University. And Qixing does a lot of interesting work in 3D and computational geometry. And today he's going to tell us about hybrid 3D representations. And for our panelists today, we have Andrew Owens from University of Michigan and Yushan Wang from UIUC. So let's get.
Okay, thank you. Thank you, Andrew, for the nice introduction. So today I'm going to talk a little bit about a series of work that I have been doing during the past 2 or 3 years. So I summarized the name called hybrid 3D representations, but I think the scope is quite broad. As you can see in the talk, it connects to many relevant stuff in vision, in machine learning, graphics, geometry, and a little bit of theory as well. So I want to start with some motivation here, right? So thinking about so this seminar series about 3D vision plus, right? So 3D vision, I think both in the core for the cortex, right? So it's recovering the underlying 3D structures from images, right? So there are a lot of cortex like post estimation, structural motion, multi-view stereo. Okay, so this has been the core of the 3D vision, but I should say that recently, in terms of the research, if you go to CVPR and look at what is related to 3D, I think we are seeing essentially a shift in terms of research focus, and really the drive for this is the emergence of the large-scale 3D repositories, like both for objects and for scenes, right? So, and because of that, so we are turning from not just for reconstructing 3D geometry, right, so three-dimensional objects, we also want to use 3D structures, right, the 3D models as a modality or to do 3D understanding. For example, right, so the cortex include classification, segmentation, detection, right? Those are the primitive ones, and there are more advanced ones, right? So one application area of this very concrete one is autonomous driving, right? So where, for example, where we have acquired a 3D point cloud of the underlying environment, and we want to understand, right, both the static objects and dynamic objects. Okay, in terms of 3D understanding, I think it was very good to compare, for example, the 2D vision, right, and 3D vision, right? From the task perspective, we all study those primitive tasks, right? Classification, segmentation, detection, right? But really, then the question here is that from the research perspective, right? So what is really fundamental difference between 2D vision and 3D vision? Clearly, there are many differences, right? So, but I want to emphasize one difference, right? Is the notion of representation, okay? Meaning that how we represent both the input data output, right, to apply machine learning algorithms. And this is interesting because if you are coming from a machine learning background, what you first learn here is that, for example, we have X and Y, right? In between, there's a mapping. And then we develop machine learning theory built on top of that. Okay. All right. Well, then the question here is that we want to solve this 3D vision problems. How are we going to represent what is X for the input and what is Y for the output, right? So that is a fundamental question we need to address. And this question is actually not trivial for three-dimensional objects, because if you think about in the literature how we represent 3D models, right? So if you have a computer graphics or geometry processing background, you should be aware of this, right? So in the graphics community, we have studied many different representations, right? For example, volumetric representations, triangular mesh representations. Then we also have other representations such as point cloud, parametric surfaces, right? So constructed solid geometry, and the multi-view light field, for example, is one example of this representation, right? We represent a three-dimensional object and the environment, right, using night field, and then we can render the more objects on different categories. And recently, people are studying, for example, semantic representation, right? So, for example, hierarchical organizations of objects and the parts, and the objects and parts have semantic meanings, right? So this is some representations that people tend to use, right? For example, for high-level semantic understanding. Okay, then the question here is that what is the right representation? What is the best representation, right? For 3D. It turns out that it's very interesting is that there's not really a single representation, okay, that works for all the tasks, okay, works for all the tasks, right? So for different applications, people tend to develop different representations. And in fact, if you go to the major computer vision conferences, right, each year, right, you can add one page of new 3D representation, right, introduced for different tasks, okay, and for improved performance, okay, here. So I also want to talk a little bit about that. So the representation is not just for like input data, like for example, how we represent 3D objects. It also matters, for example, the output. For example, right, so this is the task of 3D object detection, right? We want to output from each, take a point cloud or three-dimensional scene as input. We want to detect the object bounding boxes, right? So there are many ways to parameterize, right? So the bounding box, right? You can have a box center plus the offset along each direction. We can also detect face centers. We can also detect edge centers, right? For example, many of those representations, they do have semantic meaning, right? And so the question is very interesting question for what is the right representation, right? For even for the output. Okay, so my argument here is that instead of focusing on single representation, right? So it would be good to combine multiple representations together, right? Even for a single task, okay? So I call it the hybrid representation, right? So this notion actually originates from tasks in graphics. Let me just give you one example, okay? So for example, for collision detection, the goal here is that we have a bunch of objects represented as meshes, and we want to decide whether the objects collide with each other, right? You may imagine that this task is very important for physical simulation, right? So we want to detect collisions, right, to settle the forces, okay, for physical simulation. And this is very important for robotics and so on, okay? But the question here is that what is the right representation for collision detection? Clearly, one strategy here is that we can do this kind of face-to-face intersection check between all pairs of faces. But quickly, you'll realize that this is very time-consuming, right? And it's not that practical. It turns out that how people handle this is that they build up a spatial data structure very similar to this volumetric representation for 3D geometry. And they use this kind of so-called spatial data structure, right? For example, archery is one example. They want to use this to do this kind of accelerate the collision detection check. For example, if two cells do not overlap, then all the triangles contained in the cells do not overlap, okay? And this can greatly accelerate the computation, right? So here, this is one example where, but of course, in the end, we have to do this kind of face-to-face intersection check, right? So for a subset of face pairs, okay? So this is one example why this kind of hybrid representation is useful, right, in this case. And another example, for example, people did this, right, combining explicit representation and implicit representation for field simulation, okay? So this is another example, okay? So for understanding, we are not just using this to accelerate computation. We want to do something different, right? We want to combine the strengths of multiple representations together, right? For example, for feature learning and for variance reduction, which I will introduce next, okay? But the motivation comes from here. Okay? All right. So the common thing here is that what we want to do is that we want to build a graph of graph of representations where the nodes are different representations, and edges are either some deterministic procedures, right, solving some optimization problem, or some neural network. Okay, and And the nice thing about here is that, for example, there's some generic consistency constraints here where, for example, when you compose neural networks through different paths, right, they'll be consistent, right? So some generic constraints will introduce. Okay, so there are two types of paradigms here. I usually classify them into, for example, testing consistency and training consistency. Okay, so what the difference here is that, for example, in testing consistency, we want to do the predictions independently, and then we somehow want to enforce the consistency through different predictions of different representations to predict the final output. Okay, so in fact, one very simple example of this is the ensemble of independently trained neural networks, which I will talk about in the next few slides. So there's another paradigm I call it training consistency, right? For example, if we are familiar with cyclogram, that falls into this, right? So essentially, we are trying to formulate this kind of self-supervision as a training loss to train the individual network. Okay, so I call it training consistency because the consistency is enforced during training. Okay, so let me start with the testing consistency. So to basically summarize what we'll do here is that essentially we have different representations and we want to aggregate the predictions from different representations. So this will become clear for different tasks, which I'll talk about. Then essentially, a nice thing about this kind of over-parameterized neural network is that the predictions are uncorrelated. Then we can essentially explore this kind of uncorrelation among different representations. And of course, a very interesting aspect that you may immediately come out will raise the question is that if we introduce a hybrid representation, would this make the model more complex, right? So in fact, that and Twitter, that's a joke, right? So for all the machine learning papers, right, the model is more complex. We improve the complexity, right? So I want to also talk a little bit about this, right? So in fact, there's a very interesting trade-off between model complexity and the prediction accuracy. Okay. So the first thing I want to talk a little bit about why we actually motivate us to really study this, for example, this kind of hybrid representation is that is a notion called the double descent, right, in over-parameterization. Okay. So what usually in a standard setting, right? So there's the bias variance trade-off, right? So non-deep learning era, meaning that if you make the model more complex, right, the bias tends to reduce, variance goes up, right? So if you make the model less complex, then the bias increases, variance reduces. But in a deep learning era, in particular, for over-parameterized networks, there are people. There's a very interesting behavior called this double descent, meaning that when you increase the model size, suppose the model is significantly bigger than the amount of training data. When you increase the model, both the variance, right? So essentially, the bias will converge to something. Okay, for example, neural tangent kernel. Under some assumptions, okay, it will converge to NDK, but the variance tends to go to zero, okay, when the model size increases, right? So instead of going infinity, okay, in the standard setting, it tends to go to zero, okay? So this is considered one of the biggest achievements in the theory of deep learning. So this is very interesting in the sense that, for example, if we increase the model size, right, there are two ways to increase the model size, right? For example, consider the two-layer neural network. This is a very simple setting, but the results generalize also to other networks, right? For example, if we increase the network size from M to MT, right? For example, network V, a lot of people have studied this, right? So the bias remains approximately the same, but the variance scales as this, right? It goes to infinity, goes to zero. Okay. So this is one way to improve the network, right? So you're making the model, essentially we can interpret this as making the model under each representation bigger, right? So bigger is better, but of course in practice, you don't want to make this too big because the bigger models are hard to train, right? It may not converge to a point where those properties are satisfied, right? So you cannot make this too big. Okay, so this is one way to increase the model size, but what hybrid representation does, right? The analogy here is that instead of just using one model, we are trying to assemble multiple networks of the size P. The bias so the typo here. The bias remains the same, right? But the variance is reduced by P points. So essentially, the variance reduction rate is better, right, than increase the network size. Okay, of course there are a lot of assumptions here. Okay, so so that is very interesting, right? So meaning that instead of improving the model on each representation, it's better to consider multiple networks, right? So, and I argue that it's even better to consider multiple, not just a single representation, but multiple networks on the single representation. It's better to consider different networks on the different representation. Okay. One thing is that the bias and the different representation are different, right? So maybe you can even reduce the bias. Okay, so and then of course this is an open problem. And for example, the variance reduction, right? I will show a concrete example is right, when combining different representations, the variance reduction is more significant compared to comparing a single representation. Okay, so that is basically the motivation part. So I will give one or two concrete examples here. So this is a paper published at ECCV 1 year ago, about 1 year ago. Right, it's about 3D object detection. Right, so the task here is that we have a 3D scene and we have oriented object bounding boxes. And the goal here is that you take a 3D scene, you want to detect those. Okay, right. For example, in autonomous driving, this is a very important task. Okay, and here we focus on indoor scenes. But object detection clearly, in 2D, a lot of people have studied this. Right. So a very recent change is that we formulate object detection as a regression test. But of course, how we represent each object, right? It's very interesting, right? For example, ColorNet, like extremely send objects to points, right, done from my colleagues. Right, so this is one very recent change. And then we also have this kind of like in 3D, we have a counterpart called VoltNet, right? So you take a point cloud as input and output the object bounding boxes. But here the question, really the question here is that how we represent the object bounding box. But it turns out that with one strategy that's done in VoltNet is that we represent the object as a center and a side, right? So, but here but there may be cases, for example, like multiple objects share similar centers, right? For example, boxes and so forth and so on, right? So this one is not cannot really fully cover all the scenarios. So what we propose here is to consider multiple representations, right? Multiple ways to encode our object bounding box, right? So instead, we are predicting 19 primitives, we call it primitives, right? So those are the box centers, those are the 6 fixed centers and 12 edge centers, okay? Then we tried using, of course, the feature extraction towers are shared, okay? Then we tried this on a bunch of categories from, for example, from SunCG, from ScanNet. So what we realized is that, for example, like this kind of box centers, face centers, the edge centers, they tend to have semantic meaning, right? Meaning that, for example, right, if the object is a very solid, then box center is well defined. For example, if the object like this kind of text, right, it has prominent this kind of edge center, face centers. But it turns out that later I will show a statistic, right? It turns out that different primitives, they tend to know different features. Okay, so let me first introduce the network architecture, right? So we have this kind of backbone feature extraction towers, right? So then we have this kind of hybrid feature primitives. Then we feature descriptors. Then we use the feature descriptors to predict with the locations of object centers, locations of face centers, locations of edge centers. Then what we do is that we solve a regression problem to generate the proposals, object proposals for the bounding boxes. And right, so those are the geometric primitives we want to feed the object bounding boxes to those predicted geometric primitives. Then we do refinement, okay, classification and refinement. So nice thing about this is, right, so not only different primitives, they learn different features, but also they provide over complete set, right? For example, the object bounding box, we don't need 19 primitives. We only need, for example, 6, for example, okay, or 3, okay. And in this case, depending what type of primitives, okay. And in this case, if we have over complete set, what it means that we don't need all, right? So from the comparative sensing point of view, is that some of them can be outliers. For example, if we predict the object bounding box, the center is off, right? Center is off, but the face centers are good, right? Then we do this robust fitting, we will remove the prediction of the center as an outlier, right? We will not consider that. And this can be formulated as using some truncated L2 loss, and this can be right integrated in end-to-end training, right, back propagated through this implicit function theorem. Okay, I can do that. And then we can also aggregate the features associated with different primitives together, right? So they tend to know different features, and they provide richer features for refining, for example, the parameters of the object bounding box and so on. Okay, and this actually gets a huge boost from on the ScanNet compared to many baseline approaches. It's still one of the state-of-the-art results, okay, on this data set of the 1 year. Okay. All right, and we also get good performance on the SUN RGBD, right? So this is the difference between SUN RGBD and the ScanNet is that SUN RGBD is a single scan, right? So ScanNet is complete object, complete 3D scene. Okay. SUN RGBD, we also get some boost, not as big as the boost on ScanNet. The reason here is, of course, the data is sparse, and we argue that, for example, the labels are not as clean as ScanNet. Okay, so the boosts are consistent across with them on ScanNet, are consistent across the different categories. Of course, for the categories where the baseline approaches have already good performance, the boost is not that big. But for other categories, like CAP, right? So other categories, the boost are significant. Okay, so that is basically the empirical part, and I want to do a little bit of analysis here, right? So I think there are very interesting messages here that you may not be aware of. Okay, so the first thing, as I mentioned at the very beginning, is that even the representations, they tend to learn different features, right, and have different generalization behavior, right? So for example, like, so essentially, we predict, right, so those are the error for each type of geometric primitive associated with a particular type of object, right? So the door, so if all the features are useful, right, so they're comparable, then essentially those distributions should be very similar to each other, okay? But it turns out that the message here is that for different type of objects, they tend to, right, so some of the primitives are more accurate than the others, right? So on one object, right, then those sets, they change, of course, right? For example, there's a very big difference between, for example, table and the cabinet, right? So, and the table and chair are also different, okay? Okay, so essentially the message here is that different primitives, that right, so the generalization behavior tends to be very different across different categories. All right, another argument is that the prediction on the different representation not strongly correlated, right? So this can be interpreted from our parameterization theory, and we actually plotted on some validation set. We plotted the covariance matrix, right? So for the onto the data set, you can see that the covariance matrix, right, is close to be a diagonal matrix. Of course, there's some salient off diagonal correlations, right, for on one data set, but overall, right, you can see that the predictions are uncorrelated. Okay. And another interesting thing here is that then you may want to argue, right, what about the bias and variance, right? For example, you said I said at the very beginning, variance can be reduced, the bias is not that clear, right? But it turns out here is that if the blue box correspond to bias, the yellow box, right, the orange box corresponds variance, right? So it turns out that we tried different settings, right? It turns out that the bias is smaller. Okay, of course, it really depends on, right? We need a precise definition here. But usually the bias is smaller than the variance, meaning that in this case, right, if we can reduce the variance of the predictions, then we can improve the accuracy. Okay. Okay. So how to then I also want to talk a little bit about, right? So so the difference between this hybrid representations and, for example, in sample method, right? So in sample method, we just mostly do like simple average, right? But for this hybrid representations, what we do here, right? So even in the object detection case, is that we solve some generalized regression problem, meaning that so yi's are essentially the predictions on the different primitives, and x is what we want to estimate, for example, parameters of the object. And of course, the geometric primitives are related to x, right? So by some algebraic equation, right? Okay. And we want to solve this, right, for example, in the least square sense, robust way. Okay. In the least square sense, right? So then we can approximate x star, right? So by some linear approximation. Okay. And if we do the calculation, we can see that the variance of this, right? It really depends. Okay. So the message here, what I want to convey here is that it really depends on the configurations among the different predictions. Okay, so that is very critical, meaning that if we develop the hybrid representation so that, for example, the covariance matrix, this part, right, becomes well conditioned, then we get a huge error of the variance reduction, right? So really here is that, right, from the system perspective, how to develop the representations that the complementary to each other. Okay, right? So of course, the characteristics of variance reduction depend on the configuration among different representations. And how to do this automatically, this is still open problem. But let me give you one example, okay, why I say that the different representations can be beneficial to each other, okay? This example is the task of the sixth dimension of the post estimation, right? So we have an input object, a very simple setting, right? Suppose we know the 3D model of the object, and the output is the pose of this object, right? Very simple settings. There are more generalized settings that other speakers have introduced in this in 3D previous seminars. Okay, so this is just a simple setting. I'm using this to demonstrate the idea. Okay, so input image object, which will assume the underlying 3D object is given to us. Okay, and we want to predict its pose. So a popular framework recently, right, is that we first predict the key points, then we do post regression, right? So this can benefit from intermediate supervision, can benefit from feature learning and geometric constraints. Okay, well, the question here is that is the key point, right? So this is the ideal representation for this task, right? So we argue that it's not, right? In fact, that we can consider other representations, like even edges between the key points, right? So and also symmetry correspondences, right? They all provide some 3D cubes, right? To have some constraints that on the underlying 3D pose. Okay. So essentially, what we have analyzed is something very interesting. Okay, so for example, take a simple setting, right? We have a camera and we have the object in front of it. Suppose the object like this kind of picture, right? So it's wide, it's relatively thin, and we can do the variance reduction by fitting. It's not just the key points, but fitting the pose to key point edges between key points and symmetry correspondences. So what we realized here is that, for example, the edges between the key points actually help a lot in terms of, for example, the absolute depth. Okay, reduce the variance along that direction compared to just using a single key point. Okay, so the math is a little bit complicated, but here, what I want to convey is that, for example, the edges, right? So the delta is relatively small. It has a same component here, but the key point, right? So this component is relatively weak, right? When combining these two together, we can enhance the condition number of the Hessian. Okay, and empirically, we also justify this. Okay. So I think what I want to say here is that for this kind of 3D vision problem, right? So we do this, so this kind of local uncertainty analysis, because of predictions are uncorrelated. Okay, so that we can formulate the problem in this way. Is that in 3D, I believe that there are a lot of interesting structures here where the representations are complementary to each other. Okay, so this is one example. Okay. Then there are other examples that I have we have worked on. For example, we worked on the applications of indoor scene synthesis, right? That combines a range of objects. This is one representation and an image-based representation, so that we can learn this kind of correlations across different objects, and we get in particular the synthesis scenes have less self collision. And we apply this idea to do this kind of extreme relative pose estimation, where we want to estimate pose between two scans that do not have any overlap in vision. Okay, so this is important, for example, in loop closure detection, in like we have disruptions in this kind of scanning procedure, right? And we want to estimate scans that have very small overlap. So what we do is that here we do this scene completion so that the complete things they overlap, right? So that is a very simple idea. But then the question here is what is the right representation to do the completion, right? Because different representations tend to have different generalization behavior, and for the task of pose estimation, we do not need a very detailed completion, right? So it turns out that by combining multiple representations to do the completion, right? So the generalization behavior, we can combine the strengths of the features learned under each representation. Okay, another example is this is archive paper where we combine this kind of single view cues and multi-view cues to do multi-view stereo. And we combine, for example, semantic features, geometric constraints, and edges to do shape primitive detection. Okay, so I think, right, so there are many open questions here. Of course, for example, how to automatically determine the best set of hybrid representations, right? So that is an open challenge here. But I think, I hope I convey the message is that using different representations, right, could be very beneficial. Okay. Okay, so that is the end of the testing consistency, right? Meaning that we have different representations and then we somehow aggregate them, right? So some of the approaches, right, can be trained in the end-to-end manner, right? So combining different representations. Okay, some of them we have two stages. Okay, so this is not like testing consistency. It's not just about right. So two stages. Okay, so for example, this object detection, the network trained end to end, but the way we design the network follows this kind of paradigm of the testing consistency. Right. Okay. Now I want to talk about the training consistency. So the biggest difference here, right? So for example, testing cannot using unlabeled data. For training consistency, we'll use unlabeled data, right? So for example, cycle gas, right, by Yang et al, right? So that is one example, right? So we can use unlabeled data, and or maybe even just use unlabeled data. Okay. Okay. So here there are two advantages I want to summarize here. Right. So the one advantage of this training consistency is that we can leverage more training data. Okay, not just unlabeled data. Right. So I'll give you one example here. So this is in a different setting. Okay, different setting, but the conceptual idea is similar. Okay. So here, say we want to train a machine translator from two minor languages, right? Suppose we have insufficient training data to train the machine learning translate work. Right. So how to address this issue here is that instead of just looking at these two languages, we can introduce a major language, right? And suppose that because it's a major language, the major language usually has like the rich pair data between the major language and the minor languages, right? So people usually do that, okay? Suppose in this case, right? So we have rich pair data between the major language and the minor languages. Then we can use the rich pair data to train two neural networks, right? Then we can compose the neural networks to get the translator between the original two minor languages. And very interesting thing here is that in most cases, we cannot compose the training data. For example, a sentence in Korean has a translation in English, but that particular sentence may not have a translation property, right? We cannot compare the training data, but once we have trained the neural network, we can compose. Okay. Okay, so that is one example. Another example I may already mention, right? Is that it really allows us to leverage unlabeled data. Okay. So this is one example of a special case. If, for example, is the ensemble method. Okay. Right. For example, right, in a standard setting, we have the input, we have the output, and we want to train a neural network to do the prediction. For example, one strategy is choosing one representation, but in this case, we can only use labeled data to train the neural network. But in a joint setting, suppose we have an input, right? For example, three-dimensional object, we can consider multiple representations like point cloud, volumetric grid, parametric surfaces. Then we can design neural networks on the different representations. And then in this case, we have this unlabeled, right? So we can use unlabeled data for training, right? So when we insert unlabeled data, then we can have two different predictions on the different representations, right? But we can enforce that to be consistent, right? Intuitively, this is not rigorous proven. Is that right? So on the different representations, we tend to learn, right? So there are easy features to learn on the different representations, and those easy features tend to vary. Okay, and when we learn those kind of easy feature representations, and using unlabeled data helps us to the other representations to learn the easy features on the other representations. We intuitively can imagine this. Okay, but of course we need a rigorous understanding of this. Okay, so this is great. And then the question here is that we have all this kind of the benefits. What is the right way to integrate them together? Okay, So before introducing how to do that, I want to talk a little bit about what we have done. For example, in a very relevant problem called map synchronization. I will talk about what is that. Okay. But then I'll come back, right? So because I think the insights here are very useful, but of course the limitations in the neural network setting, we have to use completely different techniques. Okay, but I think the insights are very interesting. So here, analogy to the language example is that I want to introduce another example, and conceptually they're very similar, but have different flavor, right? So say we have two objects, and we want to compute dense correspondences between them, for example, for the application of texture transform. And what we do here is that we go to the internet, we download some software package, right? The brand intrinsic maps is one of the state of the art. We download, and then we load the model. So press the button, we get some correspondences, right? So the red are the correspondences colored in red are the ones that have large error, right? Suppose we have a way to evaluate. Then what we do here, right? So one way, what we typically do, right, before the big data era, is to read the paper, right? Read the paper and change, tune the hyperparameters and so on, right? But what about the paper is it takes time to understand, right? And in the big data era, we can address this issue very easily, right? We can just find intermediate objects and whose shape sits in between, okay, those first two objects, okay? And in this case, we don't need to tune the hyperparameters. We just need to, right? You don't need to understand the paper. We just know the object choice, the pairs choice. We press two buttons, then we get two well improved maps, right? The good maps, right? Because the input objects are more similar. Then in this case, we can just simply compose, right? We can just simply compose, right? It's very similar to the Nancy example, but different flavor, okay? Different flavor, right? So what I want to argue here is really thinking about a collection of objects here. Then we have some ways to compute pairwise maps. Some of them are good and some of them are bad. But I want to argue that the good ones are still the form of connected graph. Right? In fact, if this property is not satisfied, then we can improve the number of objects so that each object has a certain neighborhood where the maps are good. Right. Okay. If that is the case, I want to introduce the map synchronization problem, where we have a collection of objects, but in the analogy of the neural network setting, it's a collection of representations. Okay, so in this setting, we have maps between pairs of objects. In the neural network setting, we have neural networks between pairs of vertices. Okay, and some of them are good, some of them are bad. But if we can remove the bad ones, then we can use the idea of propagation to generate maps between all pairs of objects. Okay. So very interesting is that, so I have done a bunch of work on this, among others, is that for this map synchronization problem, where we can represent each map using a matrix, right? So permutations, rotations, and so on. We introduce a big matrix, right? That collects pairwise maps in blocks. Then this, right? For example, this kind of where we have this kind of a consistency constraint can be interpreted as the fact that X is represented, right? For example, this kind of composition, okay, compositional constraint, encoded as, formulated as the fact that X is no rank and positive semi-definite. And then you can think about this kind of noise measurement of matrix block, right? So as so the input maps coming out of off-the-shelf software as noise measurement, right? So this really allows us to formulate this kind of constrained matrix optimization problem to solve this. And a very nice thing about this is that we can put some theoretical guarantees. For example, if the number of incorrect measurements, right, the number of incorrect correspondences is below some threshold, then we can develop some optimization strategies to remove the noise. Okay, remove the noise. So this is very nice. Okay, this is the motivation, okay, for example, to join learning, meaning that if each individual network is hard to train, then optimizing them together, right? So we can improve. Okay, this is the analogy here. But of course, the downside of this is that, right, neural networks, they are very complicated, right? We cannot encode them using matrices, okay, and they're directed, meaning that. All right. So for example, you have a neural network may not have the inverse, right? So this meaning that we have to develop very different techniques to train them together. Okay. So I want to talk a little bit about the passive environment map network works. This is the general purpose framework, right? Meaning, suppose we have a collection of a collection of representations. We have a collection of we have neural networks between them. What is the principle to develop this kind of self-supervised supervision losses? Okay, to address this to do the network training. But of course, this generalized to special settings, okay, special settings like between pairs and between triplets. Okay, so here really the focus here is that how to do this on general graph, right? So that is the focus. Okay. Okay, so we have this multilingual translation example, right? So we introduced this example. We have 3 representations. What I want to do here is that we want to do some abstraction here, right? So that we can use the abstraction built on top of that to develop some general principles. Okay. So in this 3 representation example, we have essentially we can summarize this just using some one equation, right? So F3 equal to the composition of F2 and F1, right? So I call this path invariance. So this is somehow slightly different from cycle consistency. For example, when you compose all the maps on a cycle, it should be identity. Okay, but it turns out that in theory, there's a difference between this kind of direct graph and the graph, for example, that's strongly connected. Okay, so there's some differences here. Okay, right. Later we'll see that. So we want to have a formal definition first. Okay, so essentially we have a collection of graphs. We have some edges. You can collect all past pairs that share the source and target, right? Then we essentially say that a collection of neural networks, right? Those neural networks associated with the edges here, right? By the way, this is a graph with 7 nodes, and then we have 3-point clouds with different resolutions as 2 volumetric representations. Also, the resolution is different. Then we say that the path invariant is right. So for all the path pairs, the compositions are identical. Okay, so that is the generic property. But of course, the question here is that how to avoid enumerating all the path pairs, right? For example, if we have, for example, in domain adaptation, if we have each layer of a node here, then quickly we'll have a network with hundreds of vertices, right? So enumerating all the path pairs is infeasible. The question here is that can we actually just use a small collection of path pairs, and when we enforce the consistency along the small collection, it's identical to it induces all the path pairs. Okay. The small collection is very important for example, for formulating the training loss, right? In this case, I talk about training consistency. This really means that we will have 2 terms. The first term is essentially the loss associated with each edge, right? Without, for example, the training consistency loss, then essentially we're training each network in isolation, right, along each edge, right? Yeah, this for example in a distributed manner. But here, what we want to do is that we want to enforce the consistency along different path pairs, and this can be done using unlabeled data, right? For example, in the NANSG case, we have 2 terms for the unsupervised loss, and we have 1 term for the unsupervised loss, right? So F3 equal to F2 composition F2 and F1, right? And of course, in general, so the second term, the number of terms in unsupervised loss is equal to the number of path pairs, right? And we want to reduce that because implementing each one has a loss, right? Okay, so really the question here is that the theory question we want to address here is that what is the minimal number of path pairs so that it can induce all the path pairs, right? The consistency. Okay, to start this, we need to introduce what is the definition of induction, right? It turns out that there's 3 induction operations, right? For example, merge, right? You can merge one and merge 2 path pairs, and you can stitch 2 path pairs, and then you can also cut, okay, cut 2 path pairs, right? So those are the primitive operations that preserve the path invariance property, okay? All right. Okay, then suppose we have those three induction operations. So how many path pairs we need, right? So we have a given essential set that given a directed graph with n vertices and m edges, there exists a path invariant spaces, like collecting path pairs that can induce all the other path pairs besides at the most O n times m. Okay, n is number of vertices, m is number of edges. If you are familiar with directed graph with some cycle basis, you can immediately realize that this is bigger. Okay, this is bigger in the undirected case. Okay, but here we go give an upper bound. Okay, the main idea for the proof is that a directed graph is a cyclic graph of strongly connected components. Okay, then we can do the construction based on this way. Okay, okay, I want to briefly, if you are really interested, I just draw the connection without really talking about details, right? So, so this path invariant basis is connected to cycle basis, right? So there's a rich theory about the space of cycle basis, right? Okay. The difference between, for example, define this kind of cycle basis on directed graph is that the minimal size we know, right, is the number of edges minus number of vertices plus 1, right? M minus n plus 1, right? It's a lot smaller than in the passive, right, in the directed case. And then many conjectures. Okay, so I think the computing the smallest one, we don't know the smallest one. We have upper bound. Of course, we also have a trivial lower bound, but in between we have very little results. And then even for them testing, right? Suppose you have a collection of cycles, collection of path pairs, testing whether they can induce all the path pairs. So this is also NP-hard, okay, we believe. All right, so those are the interesting questions. And does it really work in practice? We have some very empirical, some simple results, right? So what we tried is the task of semantic segmentation. We use this network and they train the network jointly. Essentially, the message here is that we can combine 8% of label data plus 92% unlabeled data. So we can get the performance data comparable to 30% of label data on this particular data set, right? So this is encouraging, but of course, there's a long way to go, okay, to really boost the number, okay, 30% to even higher. Okay, so I also want to share a message here, right? So this is something that I found very interesting. If you are interested in the map synchronization problem, right? So I think the reason, even in computer vision, okay, I think Andrew worked a little bit, not you, Andrew Owens worked a little bit a long time ago. Okay, so this is, for example, this is related to structure from motion, okay, for 3D reconstruction. So the message, very recent message here is that recently people have been working on this no-ranked techniques, special techniques, right? So I think there's a bunch of papers at CVP on this. So here, what we found very interesting, but we don't have a proof here for very, very sparse graphs, very sparse graphs. It's better to just enforce the cycle consistency, okay, loss by detecting cycles and optimizing that. So that is more preferable than this no-rank technique, which works remarkably well on dense graphs. Okay. So the reason here is that I think for this kind of joint learning loss, it works even the spatial gap of the sparse graph is very small. Okay. For dense graph, the spatial gap is big, so that we can remove all the noise. And then for sparse graphs, the spatial gap is very small. Okay, it turns out this kind of joint loss is very useful. Okay. Of course, I should mention many other relevant works. So all the here are very influential, right? So and like Alyosha, Philip, right, Ting Hui, and so we started working on this this kind of image correspondence problem, right? So by enforcing some consistency, and this is a cyclogram paper that have been very influential, changing the field. Then we have this kind of taxonomy, which is the best paper a couple years back. then last year, there's a paper by Amir, Leo, and others on this training consistency across different 3D predictions. Okay, so if you're interested, you should look at those. Okay, so what I talked about is more from the graph theory perspective, right? So talking about how to define the loss, defining the past event spaces, and then how to construct that on general graphs. Okay. All right. So I want to talk a little bit about some feature direction. Okay, feature direction, right? So I think this is a very rich space. There are many open problems in this direction. So I'm very interested in more on this, both on the applied side and on the theory side in particular. For example, how to continuously optimize hybrid representations, right? For example, in the post-estimation case, what is the best location for the key point? Okay, it may not necessarily be this kind of semantic, right? Semantics. For example, when annotating key points. So what are the best key points that are beneficial to each other, right? For the post-estimation. So this is very interesting. It may not necessarily be the key points that are very obvious. Okay. Right. So I think how to model this kind of testing consistency among network representations. This is also very interesting, and also the trade-offs between training consistency and testing consistency. Okay. So this is also very interesting. Both the theory aspect and the practice aspect. Okay. All right, so I want to acknowledge my funding agencies, and thanks, and I'm happy to take questions, and looking forward to the panel discussion.
Thank you, Qixing. Let's see. Thank you for the nice talk.
Okay.
There hasn't been any questions on YouTube, but if you're watching, I'm happy to take questions. I'm monitoring the chat, so please ask questions. So let's see, panelists, do you have any questions? Maybe we can start with like a low-level questions or yeah, whatever you would like.
Sure. First of all, a very nice talk, Qixing. Very cool to see that line of work. So a lot of the representations you used are representations that are already in the literature. Knowing that you might use representations as part of a hybrid representation, would that change how you would design the representations in the first place?
Yeah, I think so. So this is the question that brought up for the continuous optimization, right? I think obviously the big question is that given a test, can you develop a set of representations that we can instill? Because if we do this kind of intermediate feature representations, that the space of for training is limited, right? For example, hybrid representations like key points, they actually we can generate training data for those, right? For intermediate representations, we cannot really easily generate training data for those. But the question here is that, okay, given the task, what is the space of intermediate representation we got to develop? That I don't know, right? I think it's an open question. Even for the local ones, suppose we have a set of representations, right? How to, for example, how to throw away a few ones, just keep the best ones, right? Throw away irrelevant ones. And how to optimize the intermediate representations, right? So the ones to optimize, for example, what is the best resolution, right? What are the locations of the key points? How to develop efficient this kind of right center like a box, right? So what are the best key points for author bounding box, even for each task, for each category, right? So I believe those are very different, right? Not just I believe it's not just center, okay, but center is a good starting point. So I think those ones are very interesting questions to answer. Okay, I don't have an answer yet, but for the local one, I'm working on that. So this is a great question.
Yeah. Thanks for the answer.
Yeah.
Yeah, I have a follow-up question. First,
Yeah.
thanks for teaching very insightful talk. So you talked about hybrid representation. I was wondering, given different tasks or different scenario, how should we choose what is the right representation? Or this kind of hybrid representation is actually a unifying representation we can use to deal with different tasks?
Yeah, I can give one example. For example, in the so the one thing that you can think about is that suppose we have trained all the hybrid representation together. Suppose we have a budget. For example, the total size, model size should not exceed something. Then we have to throw away some of the representations away, right? And I think one possibility is to use the variance, right? So as a guidance. For example, we can say. So this can be formulated. Okay, this is approachable, I should say, formulated by solving some optimization problem to solve the discrete problem of keeping some representations and throwing away the others. But above than this, is very challenging. I think why I put 3D here is because I think 3D, there are a lot of this kind of like Jacobian, right? So this kind of, it's related to this kind of freedom physics, right? How to build a robust multi-body system, right? So that it's very rigid. So I think this kind of 3D, we have some similarities, some analogies over there. But this is a great question. Okay, I think there are many open questions to address, right? So one way, as I mentioned, okay, is to use the variance to solve the optimization problem, okay, to select to solve the discrete problem.
Yeah, so it's also a follow-up question. In your talk, you had this theme of like, more parameterization and, you can lower variance, and then if the representations are complementary. So like, how do you know which representations go well most together?
Yeah, so I think, so this is something that we don't really have. So I think the one way we can think about this, for example, like we have multiple representations, we add the Jacobian together, right? But the Jacobian have different, for example, eigenspace, right? Meaning that along this space, it's very rigid, then the dual space is less rigid. So essentially, if this kind of spaces, they are actually orthogonal to each other, right? For different representations, then they are complementary to each other. Okay, and so this is just an answer to the local setting, right? Meaning that the variance is a single mode. So I have answers to that. For general settings where we have multiple modes, multiple peaks, right? For example, for the predictions, right? The uncertainties, then it's very complicated. It's very complicated. So the general summary here is that you want really first we need to define to solve for this kind of stable space, subspace associated with each representation. Right, for example, for the box centers, if the box prediction, right, it's very rigid. Basically the location of the box, right, this subspace is rigid, but we don't know the size, right, and so on. And for the 3D post estimation, if we use the key point, right, so essentially the depth, absolute depth, right, so this uncertainty is big, right, so we need somehow use the edges between key points to reduce the uncertainty along this direction. We can define the spatial space, then if the stable spaces are orthogonal to each other, then they're beneficial to each other. But this is not really something that novice users would like to hear. Yeah.
Great.
Yeah.
So you alluded to this a bit in your future work about how there might be trade-offs between training consistency and testing consistency. I'd love to hear more about that. Is there ever a conflict between them? Sometimes
So what I can we have some theoretical investigations on that. So what I can tell is that if we don't care about the model size, I think testing consistency is Yeah, from the theory perspective, okay, is better than training consistency. Okay. So a logic here, I can give you a logic here is that, for example, in this nearest neighbor search, right, classification, if the training data if the training data is big enough, right, we just do nearest neighbor search. But this is true appear to, for example, training a linear classifier using training data is generalized less well. But of course, in computer vision, it's the other way around, right? So this kind of nearest neighbor it does not work that well, right? But for the testing for the neural network setting, I should say that if we have a way to define how we aggregate the predictions on the each setting, then we can probably show that it's better than training all the networks together than just use one. Okay. So that is a bit disappointing. But on the other hand, for example, in training consistency, if we only want to use the network under one representation, right? So in the testing consistency, we have in doing testing, we have to pull all the networks that we train together, right? During training, that is very expensive, right? Not friendly to mobile applications at all. In the training consistency case, if we are just interested in the performance of one network, then training consistency can improve, right? For example, certainly, okay, right, it allows us to have more training data, etc. Right? So maybe just like say one word, right? So for example, in the language case, if we are allowed to carry the two networks to the modern language during testing time, we should do it, right? But during training consistency allows us just use one network during training time. Okay, so that is my yeah.
Right. So Qixing, you just mentioned the amount of training data. So when we have a lot of data, you can actually use the nearest neighbor. So I was wondering, how should we address the issue of the amount of annotated data? Do you think the training consistency and testing consistency can be a way to reduce the amount of annotated 3D data, which might be more difficult if we would like to annotate 2D data, or other alternatives we need to make effort in this direction to reduce the number of labeled data?
Yeah, so I think reduce the number of labeled data. Yeah, I can give some thoughts around this. First of all, I think training consistency is a way to reduce the number of unlabeled data, right? Here, because we can develop the self-supervision losses for the for using unlabeled data, right? I think recently there are a lot of work on self-supervised learning, a lot of work, right? So I think the general strategy here is that above this, okay, but I think it can be formulated also on the framework is that if we choose the right representation, we may have additional regularization. For example, we have some knowledge. For example, if we have intermediate representation for the height of object, we know the height of object is between 1 meter and 1.2 meters, suppose, right? Under some representations, we can insert this kind of additional supervision to regularize. But I should say that I should say that still the labeled data is always beneficial, right? So I think unlabeled data can boost the performance a bit, right? But really, I have not seen a very few tasks, right, without using any labeled data, right? We can get state-of-the-art performance compared to using labeled data, right? So here, so my answer to this in what I talked about is that on the different representations, right, using very few labeled data, or maybe sometimes unlabeled data, right, there are feature representations that some of the features, right, some type of features are easy to learn under some representations, right? Some of the features is on the other representations, and we can combine their strengths together.
Yeah.
Right.
Interesting.
Yeah.
So related to this kind of representation, I noticed that most of the representation that you've discussed are around like explicit representations, like key points, faces, edges. Have you thought about these like implicit 3D representations or coordinate-based neural networks that output SDFs or these volumetric densities and how they could kind of benefit from this?
Yeah. So we have I have some prior projects try to combine implicit representations and meshes. I think at that time probably we did not have a very good implicit representation, not before deep SDF, right? So I think implicit representations, why it has been successful is that compared to explicit ones, that we don't care about the correspondences across different objects, right? So we don't have that. For example, if we want to generate a synthesis point cloud, right? So the correspondences across different points are implicitly given to us. That turns out to be more difficult, okay, compared to the implicit representation. So I think the implicit representations, it was very interesting to combine implicit representations and explicit. Okay, I think there have been some work on for Adobe, okay, VOA and Seed. They have done some early for 3D synthesis. Okay, but in general, I feel just like how people do have been doing this for physical simulation. Okay, I think it would be very interesting to combine like those for 3D understanding. Yeah.
Yeah, I'm kind of wondering, like, because you talked about hybrid representation and using multiple of them together, but if they came from the same network, like, there's different kind of theoretical analysis on them, like, not completely, if you had these kind of implicit representations, you could be reading out different type of representations,
Yeah, so I think sharing the same network essentially changes the variance, right? Also changes the bias. Having different representations, I think I think it would be first we need to have, right, to have a really good channel to. So I'm very interested in translating those kind of, or even extending the theoretical results in our presentation to the 3D setting. But the technical challenge here is that we have not really built the platform to really redescribe those on the different representations, right? So we first need to do that. Yeah. Once we have that, then we can think about how this hybrid representations, right? So those kind of analysis will be more friendly. Okay, the insight will be more friendly to novice users. Yeah, but another point I want to make is that I think the advances in theoretical theory of deep learning, I think the many results. Okay, I have seen very recent works that people try to do this kind of using the translate our parameterization theory to shape modeling, right? So I think the shape modeling, well, originally, right? So the B-spline theory, right? So this kind of approximation theory used to right? That is the foundation of geometric modeling. But recently, I've seen works that try to redo this using deep neural networks. Right? So that is also very interesting.
Can you tell us a bit more about path invariance versus cycle consistency? What are the situations where you might want to use one versus another?
Okay, so I think path invariance is just I want to call it because sometimes like we make it like they're the same, right? They just self-superposition and not. But on the other hand, because it's from the theory perspective, okay, I think we do have wisdom on graphs. We have the theory of cycle basis. Essentially, it's a collection of cycles. When we do some combinations of them becomes another cycle, right? That is cycle basis. But we do not have this theory does not generalize at all to directed graphs. So in general, right, when talking about the graph, we have a lot of theories on undirected graphs. Okay, but for directed graphs, with them the spectral theory, which are like a lot, does not really generalize. This path consistency is another example where the traditional cycle setting does not generalize. Yeah, so that's the reason we have to introduce a different name. If they all generalize easily, we just use cycle consistency.
Thanks.
Yeah, so I have another follow-up question. Earlier, you mentioned the self-supervised learning and the great success of self-supervised learning in 2D. So I was wondering, do you think there might be similar things happening in 3D? Basically, we can learn some kind of self-supervised model.
Very interesting question. So I think in 3D, why is that in 2D, there is the difference between 3D and 2D, in my mind, is physics and geometry, right? Because we can say that the contact, right? So stable, right? So this configuration is stable, right? We can really define that. And the distance, right? The distance. So I think this space, because we have physical and geometrical properties of objects, if we have that, we can define self-supervision losses. Right? For example, A plus B equal to 1 plus 1 equal to 2, right? We can define self-supervision losses on this, right? Right. So the length of the, right? So the geometrical properties and physical properties, right? I don't have concrete examples, but imagine that this is a rich space where we can play, right? So define self-supervision losses using geometric and physical tools, right, to train neural networks.
Okay, well, I think maybe it's time for some high-level questions. I have like a very, very high-level question, because you started out this talk with saying like, CVPR right now, we're not just doing 3D reconstruction, but we're really doing 3D for 3D understanding. And I'm really curious, like in your thoughts, like what does it mean for you to understand in 3D? Like what does the understanding, 3D scenes mean for you?
Okay, I think this is quite a challenging question to answer. So my question is that I think defining understanding is for the words, right? I think we have not really completely solved the 2D, and also the 3D problem is more even more vague than the 2D. But I also want to say that maybe we can answer this question from this way, right? So what is the flavor of the 3D understanding problems compared to the flavor of the 2D understanding problems, right? I should say in 3D, we should understand the geometry and physical properties of the object more than what people do in 2D, right? In 2D, I believe it's more semantics driven, right? Of course, people say, oh, 3D, we also do semantics, right? But I should say that in many tasks, right, in 3D, from the modality perspective, right, many tasks we can just project that into a collection of images to image understanding, right? That gives us the perfectly fine semantics on the recognition task, right? I think, in fact, there's a paper that combines point cloud and the images to do 3D object detection, right, from Stanford, I think. But I think in 3D, for understanding, we want to understand geometrical properties, the distance, velocity, height, right? For example, or doing this kind of prediction, what was the occasional object after a few meters, right? For example, there'll be the collide with each other, right? So those kind of things we can do better in 3D. And then, for example, like the schedule is less stable, for example, under like heavy winds, rain, snow, right? So those kind of properties we can do more in 3D. In 2D, we can do this kind of recognition test. Okay, so that's my comment on this.
Great. All right.
Great. Well, if we're asking really high-level questions, Qixing, you have a really interesting background. You started out in more on the, if I understand, more on the graphics and the geometry processing side. And since then, your work's really grown to cover a lot of different work in 3D in general. I was wondering what kind of insights you think the computer vision community can get from the geometry processing community.
Yeah. Okay. So I think I should say that in fact that in graphics, right? When I started in graphics, so I think that in graphics, the graphic community, at least from Sigma papers, we learned a lot from vision. Okay? I think many of the papers, I have seen many instances where vision, first there's a vision paper in the 2D case, the next year we have a 3D case. So I think we learned a lot from the vision community. And we're still learning a lot from the vision community. But I think what the graphics, in particular in the 3D, right, for 3D understanding, the vision community, I think there's a community called 3D vision and geometry processing. So there was 1 year, like I looked at for example, the 3DV conference, like the core of topics, right? So the overlap, there's a lot of overlap with the core paper of symposium and geometry processing. So that, I think after that, I think many of the geometry processing people started to publish CVPR. I think that the bring in terms of, for example, different geometric modeling, how to represent the object. I think recently the CVPR papers that the best papers on that, right? Yeah. Okay, for me, I think my background, I think, well, I'm very interested in, for example, in the synchronization problem where we have a selection object, we want to build consistent maps, right? Because neural networks are maps, right? So they're mapping one domain to another domain, right? Conceptually, abstraction, I did not change my research topic. It's just like, very different manner. Right? I'm trying to, essentially, I'm trying to apply synchronization techniques to 3D prediction, right? Or recognition problems. Yeah.
Thanks.
Yeah.
Great.
Yeah, so I have a follow-up question. So what we talked about a lot of application of 3D vision. So this is high level. I was wondering what is some future application which you think might be possible because of 3D vision that coming soon?
Wow, so this is a very interesting question. I believe Andrew has a lot of comments on this, right? I think, for example, what Andrew's work on this post estimation, right, has a lot of implications like imitation learning, right? We want to learn single demonstrations, right? So I think this opens really opens the entire, right? So a lot of possibilities. I should say that two things that I have witnessed with the deep learning is very powerful. Is that it somehow combines different fields, right? For example, like we can map images to languages because if we can represent using vectors, we can do that, right? And I think for example audio, right? So Andrew Owen, right? So this is another area. I think just really deep learning opens up, right? I should say one thing that I would say that is that we should not just focus on particular community, right? Or what people have been doing. We should expand this out because I really feel like with the deep learning, right, the connecting data under different modalities. I think the space is bigger, right? Space is bigger. Right, I think 3D vision should not, right, we should build the bridges between 2D vision and 3D vision, because I believe that this can many of the recognition tasks, right, the really understanding problem, right, the recognitions for autonomous driving can benefit from both 2D techniques and 3D techniques. Yeah.
Great. Okay, well, I think that was a good point to wrap up. It was a good question. So let's thank the speaker again. Thank you, Qixing, for that.
Yeah, okay. Thank you all. Thank you, Andrew, for hosting. Okay, nice to see you. Yeah, okay, bye.